Okay, good morning. Here I've got a couple slides on the nature of light from chapter 1 of the text. And I'll start off with a slide on the wave nature of light, and then the next slide will be on the particle nature of light. So we'll first deal with light as a wave and then as particles or photons. Light is an electromagnetic wave. It's a transverse electromagnetic wave, meaning that the electric field and the magnetic field are both perpendicular to the direction of propagation, which is the z direction. And it's an electromagnetic, so we have both an electric field E and a magnetic field B. And the transverse nature can be illustrated with this picture where z is the propagation direction, and then you see we have two perpendicular axes which represent the x and y axis, and maybe the electric wave is represented in this what appears to be a vertical sort of axis, and whereas the magnetic is perpendicular to that, in phase with it in this picture, and so sort of looks like this. And you can draw some representative vectors sort of like this as B vectors and as E vectors. So let's make this diagram so you can see that B and E are always perpendicular, and they're always perpendicular to the direction of propagation. So that's the basic geometry of the electromagnetic field propagating in the z direction. It propagates in free space at the speed of light, c, which is the product of the wavelength and the frequency. When we get inside transparent materials, however, light slows down. And what happens is it propagates at a speed of v, propagation speed of v, which is c divided by n, which is always less than c, where the refractive index then is necessarily greater than 1 always. Okay, you could say that the refractive index of a vacuum is equal to 1. What happens is that as light enters a material, the frequency remains constant. And instead of the frequency changing, it is the wavelength which changes in the material. Okay, and so this equation is important to understand, that the frequency remains constant, and it's the wavelength in the material which changes. And so we can write that the wavelength in the material is v over f, but v is c by n, and therefore the wavelength in the material is lambda divided by n, where lambda is the free space. Lambda without any subscript will always be referred to as the free space wavelength, and therefore lambda by n is less than lambda. Okay, where lambda is always free space wavelength. I'll overlap my picture a little bit here. So the wavelength in the material is less than the free space wavelength. That's schematically illustrated here, where in free space we have sort of a long wavelength, and in the glass it sort of shortens up. We've got overlaps all over the place here. Visible light is in the 400, let me use a blue here. The wavelength is in the 400 to 700 nanometer range. For the infrared, lambda is greater than the 700 nanometers, and the ultraviolet, lambda is less than the 400 nanometers. Okay. We can also write this electromagnetic wave, just briefly at least, for completeness. It is a vector, and it is a function of both z and time, where z is the propagation direction. and we'll write E naught is sine, where this E naught is the amplitude, and then we'll write kz minus omega t, where k is 2 pi over lambda, and omega is 2 pi f, or 2 pi over t, the period. So this represents a traveling wave in the plus z direction. And I assume that that's all review for you, and that we could give you an equation like this in a problem set, and you could deal with the fact that the wavelength and the frequency are intertwined with k and omega. Okay, so on to looking at the particle nature of light. Okay. Here's where we're going to deal with photons. Okay, and what we'll do is we'll say that the energy of one photon, well, the fact is that if you reduce the intensity of a light wave, of light, a light beam, say, to very low values, what you'll see is that you have discrete arrivals of energy. And so the energy appears to arrive in little packets, and these have size, which is given by what we call the energy of a photon. And so what we'll do is we'll summarize that result by saying that the energy of one photon, is equal to HF, which is also hc over lambda, where h is Planck's constant. He's the guy who figured this out. And it's given as 6.626 times 10 to the minus 34 joules seconds. Let's see, the units work out on that. Joule seconds times the frequency, seconds times hertz is canceling, and I get joules for the energy of one. And so the first thing to notice is that the energy of one photon is proportional to 1 over lambda. So longer wavelengths have lower energy photons. So for example, we can calculate the energy of a photon of light in our fiber optic system with lambdas 1550 nanometers. It turns out that Hc is about equal to 2 times 10 to the minus 25th joule meters, and therefore E1 is equal to Hc over lambda, which is 2e to the minus 25 all over, let's just say 1500 here to make the numbers, 1.5 e to the minus 6. Let's see, 1500 nanometers is 1.5 microns, or minus 10 to the minus 6. So this is about 1.3 times 10 to the minus 19th joules. What we do very often is define an electron volt. One electron volt is equal to 1.6. 1 electron volt is equal to 1.6 times 10 to the minus 19th joules. And this is a convenient quantity because it represents the energy that an electron, the kinetic energy that an electron gets after it's accelerated through a potential difference of 1 volt. And it's nice because it takes us right to the quantum world, and we'll see very often that energies of photons, for example, in this quantum realm are in this same range of 10 to the minus 19th joules. And so we can write the 1.3 as 1.3 times 10 to the minus 19th joules times 1 electron volt per 1.6 times 10 to the minus 19th joules. And the joules cancel, yielding the units of electron volts, and so we get 0.81 electron volts. So electron volts are a great convenient unit of energy when we're dealing with quantum level events. So there's a quick summary of both the wave nature and the particle nature of light, basic equations. I'm assuming you've seen all these before, but here they are for you anyway. Thanks.